Preface of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Awai in November 2016. Practical Talks by an Astronomer by Harold Jacoby, Adjunct Professor of Astronomy in Columbia University. Preface. The present volume has not been designated as a systematic treatise on astronomy. There are many excellent books of that kind, suitable for serious students as well as the general reader, but they are necessarily somewhat dry and unattractive because they must aim at completeness. Completeness means detail, and detail means dryness. But the science of astronomy contains subjects that admit of detached treatment, and as many of these are precisely the ones of greatest general interest, it has seemed well to select several, and describe them in language free from technicalities. It is hoped that the book will thus prove useful to persons who do not wish to give the time required for a study of astronomy as a whole, but who may take pleasure in devoting a half hour now and then to a detached essay on some special topic. Preparation of the book in this form has made it suitable for prior publication in periodicals, and the several essays have in fact all been printed before. But the intention of collecting them into a book was kept in mind from the first, and while no attempt has been made at consecutiveness, it is hoped that nothing of merely ephemeral value has been included. End of preface.
Chapter 1 of Practical Talks by an Astronomer. This is a LibriVox recording, or LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Practical Talks by an Astronomer by Harold Jacoby. Chapter 1. Navigation at Sea. A short time ago, the writer had occasion to rummage among the archives of the Royal Astronomical Society in London to consult, if possible, the original manuscripts left by one Stephen Groombridge, an English astronomer of the good old days who died in 1832. It was known that they had been filed away about a generation ago by the late Sir George Airy, who was Astronomer Royal of England between the years 1835 and 1881. After a long search, a large and dusty box was found and opened. It was filled with documents, of which the topmost was in Sir George's own handwriting, and began substantially as follows. List of articles within this box. Number 1, this list. Number 2, etc., etc. Astronomical precision can no further go. He had listed even the list itself. Truly Airy was rightly styled Prince of Precisions. A worthy Astronomer Royal was he, to act under the royal warrant of Charles II, who established the office in 1675. Down to this present day that warrant still makes it a duty of His Majesty's astronomer to, quote, apply himself with the utmost exact care and diligence to the rectifying of the tables of the motions of the heavens and the places of the fixed stars, in order to find out the so much desired longitude at sea, for the perfecting the art of navigation. End of quote. The so much desired longitude at sea is indeed a vastly important thing to a maritime nation like England, and only in comparatively recent years has it become possible and easy for vessels to be navigated with safety and convenience upon long voyages. The writer was well acquainted with an old sea captain of New York, who had commanded one of the earliest transatlantic steamers, and who died only a few years ago. He had a goodly store of ocean yarn fit and ready for the spinning, if he could find someone who, like himself, had known and loved the ocean. In his early sea-going days, only the wealthiest of captains owned chronometers. This instrument is now considered indispensable in navigation, but at that time it was a new invention, very rare and costly, Upon a certain voyage from England to Rio Janeiro in South America, the old captain could remember the following odd method of navigation. The ship was steered by compass to the southward and westward, more or less, until the skipper's antique quadrant showed they had about reached the latitude of Rio. Then they swung her on a course due west by compass, and away she went for Rio, relying on the lookout man forward to keep the ship from running ashore. For after a certain lapse of time, being ignorant of the longitude, they could not know whether they would raise the land within an hour or in 6 weeks. We are glad of an opportunity to put this story on record, for the time is not far distant when there will be no man left among the living who can remember how ships were taken across the seas in the good old days before chronometers. Anyone who has ever been a passenger on a great transatlantic liner of today knows what an important, imposing personage is the brass-bound skipper. A very different creature is he on the deck of his ship from the modest seafaring man we meet on land, clad for the time being in his shore-going togs. But the captain's dignity is not all brass buttons and gold braid. He has behind him the powerful support of a deep, delightful mystery. He it is who takes the sun at noon and finds out the ship's path at sea, and in truth, regarded merely as a scientific experiment, the guiding of a vessel across the unmarked trackless ocean has few equals within the whole range of human knowledge. It is our purpose here to explain quite briefly the manner in which this seeming impossibility is accomplished. We shall not be able to go sufficiently into details to enable him who reads to run and navigate a magnificent steamer, but we hope to diminish that small part of the captain's vast dignity which depends upon his mysterious operations with the sextant. To begin, then, with the sextant itself. It is nothing but an instrument with which we can measure how high up the sun is in the sky. Now, everyone knows that the sun slowly climbs the sky in the morning, reaches its greatest height at noon, and then slowly sinks again in the afternoon. The captain simply begins to watch the sun through the sextant shortly before noon, and keeps at it till he discovers the sun is just beginning to descend. That is the instant of noon on the ship. The captain quickly glances at the chronometer, or calls out noon to an officer who is near that instrument, and so the error of the chronometer becomes known then and there, without any further astronomical calculations whatever. Navigators can also find the chronometer error by sextant observations when the sun is a long way from noon. The methods of doing this are somewhat less simple than for the noon observation. They belong to the details of navigation into which we cannot enter here. Incidentally, the captain also notes with the sextant how high the sun was in the sky at the noon observation. He has in his mysterious chart room some printed astronomical tables, which tell him in what terrestrial latitude the sun will have precisely that height on that particular day of the year. Thus the terrestrial latitude becomes known easily enough, and if only the captain could get his longitude too, he would know just where his ship was that day at noon. We have seen that these sextant observations furnish the error of the chronometer according to the ship's time. In other words, the captain is in possession of the correct local time in the place where the ship actually is. Now, if he also had the correct time at that moment of some well-known place on shore, he would know the difference in time between that place on shore and the ship. But every traveller by land or sea is aware that there are always differences of time between different places on the earth. If a watch be right on leaving New York, for instance, it will be much too fast on arriving at Chicago or San Francisco. The farther you go, the larger becomes the error of your watch. In fact, if you could find out how much your watch had gone into error, you would, in a sense, know how far east or west you had travelled. Now, the captain's chronometer is set to correct Greenwich time on shore, before the ship leaves port. His observations having then told him how much this is wrong on that particular day, and in that particular spot where the ship is, he knows at once just how far he has travelled east or west from Greenwich. In other words, he knows his longitude from Greenwich, for longitude is nothing more than distance from Greenwich in an east-west direction, just as latitude is only distance from the equator measured in a north-south direction. Greenwich Observatory is usually selected as the beginning of things for measuring longitudes, because it is almost the oldest of existing astronomical establishments, and belongs to the most prominent maritime nation, England. One of the most interesting bits of astronomical history was enacted in connection with this matter of longitude. From what has been said, it is clear that the ship's longitude will be obtained correctly only if the chronometer has kept exact time since the departure of the ship from port. Even a very small error of the chronometer will throw out the longitude a good many miles, and we can understand readily that it must be difficult in the extreme to construct a mechanical contrivance capable of keeping exact time when subjected to the rolling and pitching of a vessel at sea. It was as recently as the year 1736 that the first instrument capable of keeping anything like accurate time at sea was successfully completed. It was the work of an English watchmaker named John Harrison, and is one of the few great improvements in matters scientific which the world owes to a desire for winning a money prize. It appears that in 1714 a committee was appointed by the House of Commons, with no less a person than Sir Isaac Newton himself as one of its members, to consider the desirability of offering governmental encouragement for the invention of some means of finding the longitude at sea. Finally, the British government offered a reward of $50,000 for an instrument which would find the longitude within 60 miles, $75,000 if within 40 miles, and $100,000 if within 30 miles. Harrison's chronometer was finished in 1736, but he did not receive the final payment of his prize until 1764. We shall not enter into a detailed account of the vexatious delays and official procedures to which he was forced to submit during those 28 long years. It is a matter of satisfaction that Harrison lived to receive the money which he had earned. He had the genius to plan and master intricate mechanical details, but perhaps he lacked in some degree the ability of tongue and pen to bring them home to others. This may be the reason he is so little known, though it was his fortune to contribute so large and essential a part to the perfection of modern navigation. Let us hope this brief mention may serve to recall his memory from oblivion, even for a fleeting moment, that we may not have written in vain of that longitude to which his life was given. End of Chapter 1.
Chapter 2 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Practical Talks by an Astronomer by Harold Jacoby. Chapter 2, The Pleiades. Famed in legend, sung by early minstrels of Persia and Hindustan, quote, like a swarm of fireflies tangled in a silver braid, unquote. Yonder distant misty little cloud of Pleiades has always won and held the imagination of men. But it was not only for the inspiration of poets, for quickening fancy into song, that the 7 daughters of Atlas were fixed upon the firmament. The problems presented by this group of stars to the unobtrusive scientific investigator are among the most interesting known to astronomy. Their solution is still very incomplete, but what we have already learned may be counted justly among the richest spoils brought back by science from the stored treasure house of nature's secrets. The true student of astronomy is animated by no mere vulgar curiosity to pry into things hidden. If he seeks the concealed springs that move the complex visible mechanism of the heavens, he does so because his imagination is roused by the grandeur of what he sees, and deep down within him stirs the true love of the artist for his art. For it is indeed a fine art, that science of astronomy. It can have been no mere chance that has masked the Pleiades from among their fellow stars. Men of ordinary eyesight see but half a dozen distinct objects in the cluster. Those of acuter vision can count 14, but it is not until we apply the space-penetrating power of the telescope that we realize the extraordinary scale upon which the system of the Pleiades is constructed. With the Paris instrument, Wolf in 1876 catalogued 625 stars in the group, and the searching photographic survey of Henry in 1887 revealed no less than 2,326 distinct stars within and near the filmy gauze of nebulous matter always so conspicuous a feature of the Pleiades. The means at our disposal for the study of stellar distances are but feeble. Only in the case of a very small number of stars have we been able to obtain even so much as an approximate estimate of distance. The most powerful observational machinery, though directed by the tried skill of experience, has not sufficed to sound the profounder depths of space. The Pleiad stars are among those for which no measurement of distance has yet been made, so that we do not know whether they are all equally far away from us. We see them projected on the dark background of the celestial vault, but we cannot tell from actual measurement whether they are all situated near the same point in space. It may be that some are immeasurably closer to us than are the great mass of their companions. Possibly we look through the cluster at others far behind it, clinging, as it were, to the very fringe of the visible universe. Farther on we shall find evidence that something like this really is the case. But under no circumstances is it reasonable to suppose that the whole body of stars can be strung out at all sorts of distances near a straight line pointing in the direction of the visible cluster. Such a distribution may perhaps remain among the possibilities, so long as we cannot measure directly the actual distances of the individual stars. But science never accepts a mere possibility, against which we can marshal strong circumstantial evidence. We may conclude on general principles that the gathering of these many objects into a single close assemblage denotes community of origin and interests. The Pleiades, then, really belong to one another. What is the nature of their mutual tie? What is their mystery, and can we solve it? The most obvious theory is, of course, suggested by what we know to be true within our own solar system. We owe to Newton the beautiful conception of gravitation, that unique law by means of which astronomers have been enabled to reduce to perfect order the seeming tangle of planetary evolutions. The law really amounts, in effect, to this: all objects suspended within the vacancy of space attract or pull one another. How they can do this without a visible connecting link between them is a mystery which may always remain unsolved. But mystery as it is, we must accept it as an ascertained fact. It is this pull of gravitation that holds together the sun and planets, forcing them all to follow out their due and proper paths, and so to continue throughout an unbroken cycle until the great survivor, time, shall be no more. This same gravitational attraction must be at work among the Pleiades. They, too, like ourselves, must have bounds and orbits set and interwoven, revolutions and gyrations far more complex than the solar system knows. The visual discovery of such motion of rotation among the Pleiades may be called one of the pressing problems of astronomy today. We feel sure that the time is ripe, and that the discovery is actually being made at the present moment, for a generation of men is not too great a period to call a moment when we have to deal with cosmic time. It is indeed the lack of observations extending through sufficient centuries that stays our hand from grasping the coveted result. The Pleiades are so far from us that we cannot be sure of changes among them. Magnitudes are always relative. It matters not how large the actual movements may be. If they are extremely small in comparison with our distance, they must shrink to nothingness in our eyes. Trembling on the verge of invisibility, elusive, they are in that borderland where science as yet but feels her way though certain that the way is there. The foundations of exact modern knowledge of the group were laid by Bessel about 1840. With the modesty characteristic of the great, he says quite simply that he has made a number of measures of the Pleiades, thinking that the time may come when astronomers will be able to find some evidence of motion. In this unassuming way he prefaces what is still the classic model of precision and thoroughness in work of this kind. Bessel cleared the ground for a study of interstellar motion within the close star clusters, and it is probable that only by such study may we hope to demonstrate the universality of the law of gravitation in cosmic space. Bessel's acuteness in forecasting the direction of coming research was amply verified by the work of Elkin in 1885 at Yale College. Provided with a more modern instrument, but similar to Bessel's, Elkin was able to repeat his observations with a slight increase of precision. Motions in the interval of 45 years, sufficiently great to hint at coming possibilities, were shown conclusively to exist. 6 stars, at all events, have been fairly excluded from the group on account of their peculiar motions shown by Elkin's research. It is possible that they are merely seen in the background through the interstices of the cluster itself, or they may be suspended between us and the Pleiades, in either case having no real connection with the group. Finally, these observations make it reasonably certain that many of the remaining mass of stars really constitute a unit aggregation in space. Astronomers of a coming generation will again repeat the Besselian work. At present, we have been able to use his method only for the separation from the true Pleiades of chance stars that happen to lie in the same direction. Let us hope that man shall exist long enough upon this earth to see the clustered stars themselves begin and carry out such gyrations as gravitation imposes. These will doubtless be of a kind not even suggested by the lesser complexities of our solar system, for the most wonderful thing of all about the Pleiades seems to point to an intricacy of structure whose details may be destined to shake the confidence of the profoundest mathematician. There is an extraordinary nebulous condensation that seems to pervade the entire space occupied by the stellar constituents of the group. The stars are swimming in a veritable sea of luminous cloud. There are filmy, tenuous places, and again condensing whirls of material doubtless still in the gaseous or plastic stage. Most noticeable of all are certain almost straight lines of nebula that connect series of stars. In one case, shown upon a photograph made by Henry at Paris, 6 stars are strung out upon such a hazy line. We may give play to fancy, and see in this the result of some vast eruption of gaseous matter that has already begun to solidify here and there into stellar nuclei. But sound science gives not too much freedom to mere speculative theories. Her duty has been found in quiet research, and her greatest rewards have flowed from imaginative speculation only when tempered by pure reason. End of chapter 2.
Chapter 3 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marty on the Central Coast of California. Practical Talks by an Astronomer by Harold Jacoby. The Pole Star. One of the most brilliant observations of the last few years is Campbell's recent discovery of the triple character of this star. Centuries and centuries ago, when astronomy, that venerable ancient among the sciences, was but an infant, the pole star must have been considered the very oldest of observed heavenly bodies. In the beginning it was the only sure guide of the navigator at night, just as to this day it is the foundation stone for all observational stellar astronomy of precision. There has never been a time in the history of astronomy when the pole star might not have been called the most frequently measured object in the sky of night. So it is indeed strange that we should find out something altogether new about it after all these ages of study. But the importance of the discovery rests upon a surer foundation than this. The method by which it has been made is almost a new one in the science. A generation ago, men thought the perfect science, for so we love to call astronomy, could advance only by increasing a little the exact precision of observation. The citadel of perfect truth might be more closely invested, the forces of science might push forward step by step, the machinery of research might be strengthened, but that a new engine of investigation would be discovered capable of penetrating where no telescope can ever reach, this, indeed, seemed far beyond the liveliest hope of science. Even the discoverer of the spectroscope could never have dreamed of its possibilities, could never have foreseen its successes, its triumphs. The very name of this instrument suggests mystery to the popular mind. It is set down at once among the things too difficult, too intricate, too abstruse to understand. Yet in its essentials there is nothing about the spectroscope that cannot be made clear in a few words. Even the modern undulatory theory of light itself is terrible only in the length of its name. Anyone who has ever seen the waves of ocean roll, and ever again roll in upon the shore, can form a very good notion of how light moves. 'Tis just such a series of rolling waves, started perhaps from some brilliant constellation far out upon the confining bounds of the visible universe, or perhaps coming from a humble light upon the student's table. Yet it is never anything but a succession of rolling waves. Only, unlike the waves of the sea, light waves are all excessively small. We should call one whose length was a 20,000th of an inch a big one. Now the human eye possesses the property of receiving and understanding these little waves. The process is an unconscious one. Let but a set of these tiny waves roll up, as it were, out of the vast ocean of space and impinge upon the eye, and all the phenomena of light and color become what we call visible. We see the light. And how does all this find an application in astronomy? Not to enter too much into technical details, we may say that the spectroscope is an instrument which enables us to measure the length of these light waves, though their length is so exceedingly small. The day has indeed gone by when that which poets love to call the book of nature was printed in type that could be read by the eye unaided. Telescope, microscope, and spectroscope are essential now to him who would penetrate any of nature's secrets. But measurements with a telescope, like eye observations, are limited strictly to determining the directions in which we see the heavenly bodies. Ever since the beginning of things, when old Hippocrates and Ulugh Beg made the first rude but successful attempts to catalogue the stars, the eye and telescope have been able to measure only such directions. We aim the telescope at a star, and record the direction in which it was pointed. Distances in astronomy can never be measured directly. All that we know of them has been obtained by calculations based upon the Newtonian law of gravitation and observations of directions. Now the spectroscope seems to offer a sort of exception to this rule. Suppose we can measure the wavelengths of the light sent us from a star. Suppose again that the star itself, moving swiftly toward us through space, while continually setting in motion the waves of light that are ultimately to reach the waiting astronomer. Evidently the light waves will be crowded together somewhat on account of the star's motion. More waves per second will reach us than would be received from a star at rest. It is as though the light waves were compressed or shortened a little. And if the star is leaving us, instead of coming nearer, opposite effects will occur. We have then but to compare spectroscopically starlight with some artificial source of light in the observatory in order to find out whether the star is approaching us or receding from us. and by a simple process of calculation, this stellar motion could be obtained in miles per second. Thus, we can now actually measure directly, in a certain sense, linear speed in stellar space, though we are still without the means of getting directly at stellar distances. But the most wonderful thing of all about these spectroscopic measures is the fact that it makes no difference whatever how far away is the star under observation. What we learn through the spectroscope comes from the study of the waves themselves, and it is of no consequence how far they have traveled, or how long they have been a-coming. For it must not be supposed that these waves consume no time in passing from a distant star to our own solar system. It is true that they move exceedingly fast. Certainly 180,000 miles per second may be called rapid motion. But if this cosmic velocity of light is tremendous, so also are cosmic distances correspondingly vast. Light needs to move quickly from a star, for even at a rate of motion we have mentioned, it requires many years to reach us from some of the more distant constellations. It has been well said that an observer on some faraway star, if endowed with the power to see at any distance, however great, might at this moment be looking on the Crusaders proceeding from Europe against the Saracen at Jerusalem. For it is quite possible that not until now has the light which would make the earth visible had time to reach him. Yet distant as such an observer might be, light from the star on which he stood could be measured in the spectroscope, and would infallibly tell us whether the earth and the star are approaching in space or gradually drawing farther asunder. The pole star is not one of the more distant stellar systems. We do not know how far it is from us very exactly, but certainly not less than 40 or 50 years are necessary for its light to reach us. The star might have gone out of existence 20 years ago, and we not yet know of it, for we would still be receiving the light which began its long journey to us about 1850 or 1860. But no matter what may be its distance, Campbell found by careful observations made in the latter part of 1896 that the pole star was then approaching the earth at a rate of about 12 miles per second. So far there was nothing especially remarkable, but in August and September of the present year 26 careful determinations were made, and these showed that now the rate of approach varied between about 5 and 9 miles per second. More astonishing still, there was a uniform period in the changes of velocity. In about 4 days the rate of motion changed from about 5 to 9 miles and back again, and this variation kept on with great regularity. Every successive period of 4 days saw a complete cycle of velocity change forward and back between the same limits. There can be but one reasonable explanation. This star must be a double or binary star, the two components under the influence of powerful mutual gravitational attraction must be revolving in a mighty orbit. Yet this vast orbit as a whole, with the two great stars in it, must be approaching our part of the universe all the time. For the spectroscope shows the velocity of approach to increase and diminish, indeed, but it is always present. Here, then, is the great stellar system, having a 4-day revolution of its own, and yet swinging rapidly through space in our direction. Nor is this all. One of the component stars must be nearly or quite dark, else its presence would infallibly be detected by our instruments. And now we come to the most astonishing thing of all. How comes it that the average rate of approach of the 4-day system as a whole changed between 1896 and 1899? In 1896 only this velocity of the whole system was determined, the 4-day period remaining undiscovered until the more numerous observations of 1899. But even without considering the 4-day period, the changing velocity of the entire system offers one of those problems that exact science can treat only by the help of the imagination. There must be some other great center of attraction, some cosmic giant holding the visible double pole star under its control. Thus, that which we see and call the pole star is in reality threading its path about the third and greatest member of the system, itself situated in space we know not where. End of chapter 3. Recording by Marty on the Central Coast of California.
Chapter 4 of Practical Talks by an Astronomer. This is the LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Practical Talks by an Astronomer by Harold Jacoby. Chapter 4. Nebulae. Scattered about here and there among the stars are certain patches of faint luminosity called by astronomers nebulae. These little clouds of filmy light are among the most fascinating of all the kaleidoscopic phenomena of the heavens, for it needs but a glance at one of them to give the impression that here before us is the stuff of which worlds are made. All our knowledge of nature leads us to expect in her finished work the result of a series of gradual processes of development. Highly organized phenomena such as those existing in our solar system did not spring into perfection in an instant. Influential forces, easy to imagine but difficult to define, must have directed the slow, sure transformation of elemental matter into sun and planets, things and men. Therefore, a study of those forces and of their probable action upon nebular material has always exerted a strong attraction upon the acutest thinkers among men of exact science. Our knowledge of the nebulae is of two kinds: that which has been ascertained from observation as to their appearance, size, distribution, and distance, and that which is based upon hypotheses and theoretical reasoning about the condensation of stellar systems out of nebular masses. It so happens that our observational material has received a very important addition quite recently through the application of photography to the delineation of nebulae, and this we shall describe further on. Two nebulae only are visible to the unaided eye. The brighter of these is in the constellation Andromeda. It is of oval or elliptical shape and has a distinct central condensation or nucleus. Upon a photograph by Roberts, it appears to have several concentric rings surrounding the nebula proper, and gives the general impression of a flat round disk foreshortened into an oval shape on account of the observer's position not being square to the surface of the disk. Very recent photographs of this nebula, made with the 3-foot reflecting telescope of the Lick Observatory, bring out the fact that it is really spiral in form, and that the outlying nebulous rings are only parts of the spires in a great cosmic whirl. This Andromeda Nebula is the one in which the temporary star of 1885 appeared. It blazed up quite suddenly near the apparent center of the nebula, and continued in view for 6 months, fading finally beyond the reach of our most powerful telescopes. There can be little doubt that the star was actually in the nebula and not merely seen through it, though in reality situated in the extreme outlying parts of space at a distance immeasurably greater than that separating us from the nebula itself. Such an accidental superposition of nebula and star might even be due to sudden incandescence of a new star between us and the nebula. In such a case, we should see the star projected upon the surface of the nebula, so that the superposition would be identical with that actually observed. Therefore, while it is indeed possible that the star may have been either far behind the nebula or in front of it, we must accept as more probable the supposition that there was a real connection between the two. In that case, there is little doubt that we have actually observed one of those cataclysms that mark successive steps of cosmic evolution. We have no thoroughly satisfactory theory to account for such an explosive catastrophe within the body of the nebula itself. The other naked eye nebula is in the constellation Orion. In the telescope it is a more striking object perhaps than the Andromeda Nebula, for it has no well-defined geometrical form, but consists of an immense odd-shaped mass of light enclosing and surrounding a number of stars. It is unquestionably of a very complicated structure, and is therefore less easily studied and explained than the nebulae of simpler form. There is no doubt that the Orion Nebula is composed of luminous gas, and is not merely a cluster of small stars too numerous and too near together to be separated from each other, even in our most powerful telescopes. It was indeed supposed until about 40 years ago that all the nebulae are simply irresolvable star clusters, but we now have indisputable evidence derived from the spectroscope that many nebulae are composed of true gases, similar to those with which we experiment in chemical laboratories. This spectroscopic proof of the gaseous character of nebulae is one of the most important discoveries contributed by that instrument to our small stock of facts concerning the structure of the sidereal universe. Coming now to the smaller nebulae, we find a great diversity of form and appearance. Some are ring-shaped, perhaps having a less brilliant nebulosity within the ring. Many show a central condensation of disc-like appearance, planetary nebulae, or have simply a star at the center, nebulous stars. Altogether, about 10,000 such objects have been catalogued by successive generations of astronomers since the invention of the telescope, and most of these have been reported as oval in form. Now we have already referred to the important addition to our knowledge of the nebulae obtained by recent photographic observations, and this addition consists in the discovery that most of these oval nebulae are in reality spirals. Indeed, it appears that the spiral type is the normal type, and that nebulae of irregular or other forms are exceptions to the general rule. Even the great Andromeda Nebula, as we have seen, is now recognized as a spiral. The instrument with which its convolute structure was discovered is a 3-foot reflecting telescope made by Common of England, and now mounted at the Lick Observatory in California. The late Professor Keeler devoted much of his time to photographing nebulae during the last year or two. He was able to establish the important fact just mentioned, that most nebulae, formerly thought to be mere ovals, turn out to be spiral when brought under the more searching scrutiny of the photographic plate applied at the focus of a telescope of great size, and with an exposure to the feeble nebular light extending through 3 or 4 consecutive hours. Many of the spirals have more than a single volute. It is as though one were to attach a number of very flexible rods to an axle, like spokes of a wheel without a rim, and then revolve the axle rapidly. The flexible rods would bend under the rapid rotation and form a series of spiral curves not unlike many of these nebulae. Indeed, it is impossible to escape the conviction that these great celestial worlds are whirling around an axis. And it is most important in the study of the growth of worlds to recognize that the type specimen is a revolving spiral. Therefore, the rotating, flattened globe of incandescent matter postulated by Laplace's nebula hypotheses would make of our solar system an exceptional world, and not a type of stellar evolution in general. Keeler's photographs have taught us one thing more. Scarcely is there a single one of his negatives that does not show nebulae previously uncatalogued. It is estimated that if this process of photography could be extended so as to cover the entire sky, the whole number of nebulae would add up to the stupendous total of 120,000, and of these the great majority would be spiral. When we approach the question of the distribution of nebulae in different parts of the sky, as shown by their catalogued position, we are met by a curious fact. It appears that the region in the neighborhood of the Milky Way is especially poor in nebulae, whereas these objects seem to cluster in much larger numbers about those points in the sky that are farthest from the Milky Way. But we know that the Milky Way is richer in stars than any other part of the sky, since it is, in fact, made up of stellar bodies clustered so closely that it is well nigh impossible to see between them in the denser portions. Now, it cannot be the result of chance that the stars should tend to congregate in the Milky Way, while the nebulae tend to seek a position as far from it as possible. Whatever may be the cause, we must conclude that the sidereal system, as we see it, is in general constructed upon a single plan, and does not consist of a series of universes scattered at random throughout space. If we are to suppose that nebulae turn into stars as a result of condensation or any other change, then it is not astonishing to find a minimum of nebulae where there is a maximum of stars, since the nebulae will have been consumed, as it were, in the formation of the stars. It is never advisable to push philosophical speculation very far when supported by too slender a basis of fact. But if we are to regard the visible universe as made up on the whole of a single system of bodies, we may well ask one or two questions to be answered by speculative theory. We have said the stars are not uniformly distributed in space. Their concentration in the Milky Way, forming a narrow band dividing the sky into two very nearly equal parts, must be due to their being actually massed in a thin disk or ring of space within which our solar system is also situated. This thin disk projected upon the sky would then appear as the narrow star band of the Milky Way. Now, suppose this disk had an axis perpendicular to itself, and let us imagine a rotation of the whole sidereal system about that axis. Then the fact that the visible nebulae are congregated far from the Milky Way means that they are actually near the imaginary axis. Possibly the diminished velocity of motion near the axis may have something to do with the presence of nebulae there. Possibly the nebulae themselves have axes perpendicular to the plane of the Milky Way. If so, we should see the spiral nebulae near the Milky Way edgewise, and those far from it without foreshortening. Thus, the paucity of nebulae near the Milky Way may be due in part to the increased difficulty of seeing them when looked at edgewise. Indeed, there is no limit to the possibilities of hypothetical reasoning about the nebular structure of our universe. Unfortunately, the whole question must be placed for the present among the intensely interesting cosmic problems awaiting elucidation. Let us hope in this new century. End of chapter 4.
Chapter 5 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Betty B. Practical Talks by an Astronomer by Harold Jacoby. Chapter 5. Temporary Stars. Nothing can be more erroneous than to suppose that the stellar multitude has continued unchanged throughout all generations of men. Eternal fires poets have called the stars, yet they burn like any little conflagration on the earth, now flashing with energy, brilliant, incandescent, and again sinking into the dull glow of smoldering, half-burned ashes. It is even probable that space contains many darkened orbs, stars that may have risen in constellations to adorn the skies of prehistoric time, now cold, unseen, unknown. So far from dealing with an unvarying universe, it is safe to say that sidereal astronomy can advance only by the discovery of change. Observational science watches with untiring industry, and night hides few celestial events from the ardent scrutiny of astronomers. Old theories are tested and newer ones often perfected by the detection of some slight and previously unsuspected alteration upon the face of the sky. The interpretation of such changes is the most difficult task of science. It has taxed the acutest intellects among men throughout all time. If, then, changes can be seen among the stars, what are we to think of the most important change of all, the blazing into life of a new stellar system? 15 times since men began to write their records of the skies has the birth of a star been seen. Surely we may use this term when we speak of the sudden appearance
of a brilliant luminary where nothing visible existed before, but we shall see further on that scientific considerations make it highly probable that the phenomenon in question does not really involve the creation of new matter. It is old material becoming suddenly luminous for some hidden reason. In fact, whenever a new object of great brilliancy has been discovered, it has been found to lose its light again quite soon, ending either in total extinction or at least in comparative darkness. It is for this reason that the name temporary star has been applied to cases of this kind. The first authenticated instance dates from the year 134 B.C., when a new star appeared in the constellation Scorpio. It was this star that led Hipparchus to construct his stellar catalogue, the first ever made. It occurred to him, of course, that there could be but one way to make sure in the future that any given object discovered in the sky was new. It was necessary to make a complete list of everything visible in his day. Later astronomers need then only compare Hipparchus's catalogue with the heavens from time to time in order to find out whether anything unknown had appeared. This work of Hipparchus became the foundation of sidereal study and led to most important discoveries of various kinds. But no records remain concerning his new star except the bare fact of its appearance in Scorpio. Hipparchus's published works are all lost. We do not even know the exact place of his birth, and as for those due dates of entry and exit that history attaches to great names, we have them not. Yet he was easily the first astronomer of antiquity, one of the first of all time, and we know of him only from the writings of Ptolemy, who lived 300 years after him. More than 5 centuries elapsed before another temporary star was entered in the records of astronomy. This happened in the year 389 A.D., when a star appeared in Aquila, and of this one also we know nothing further. But about 12 centuries later, in November 1572, a new and brilliant object was found in the constellation Cassiopeia. It is known as Tycho Star, since it was the means of winning for astronomy a man who will always take high rank in her annals, Tycho Brahe of Denmark. When he first saw this star it was already very bright, equaling even Venus at her best, and he continued a careful series of observations for 16 months, when it faded finally from his view. The position of the new star was measured with reference to other stars in the constellation Cassiopeia, and the results of Tycho's observations were finally published by him in the year 1573. It appears that much urging on the part of friends was necessary to induce him to consent to this publication, not because of a modest reluctance to rush into print, but for the reason that he considered it undignified for a nobleman of Denmark to be the author of a book. An important question in cosmic astronomy is opened by Tycho's star. Did it really disappear from the heavens when he saw it no more, or had its luster simply been reduced below the visual power of the unaided eye? Unfortunately, Tycho's observations of the star's position in the constellation were necessarily crude. He possessed no instruments of precision such as we now have at our disposal, and so his work gives us only a rather rough approximation of the true place of the star. A small circle might be imagined on the sky of a size comparable with the possible errors of Tycho's observations. We could then say with certainty that his star must have been situated somewhere within that little circle, but it is impossible to know exactly where. It happens that our modern telescopes reveal the existence of several faint stars within the space covered by such a circle. Any one of these would have been too small for Tycho to see, and therefore any one of them may be his once brilliant luminary, reduced to a state of permanent or temporary semi-darkness. These considerations are indeed of great importance in explaining the phenomena of temporary stars. If Tycho had been able to leave us a more exact determination of his star's place in the sky, and even if our most powerful instruments could not show anything in that place today, we might nevertheless theorize on the supposition that the object still exists, but has reached a condition almost entirely dark. Indeed, the latest theory classes temporary stars among those known as variable. For many stars are known to undergo quite decided changes in brilliancy. Possibly inconstancy of light is the rule rather than the exception. But while such changes, when they exist, are too small to be perceptible in most cases, there is certainly a large number of observable variables, subject to easily measurable alterations of light. Astronomers prefer to see in the phenomena of temporary stars simple cases of variation in which the increase of light is sudden and followed by a gradual diminution. Possibly there is then a long period of comparative or even complete darkness, to be followed as before by a sudden blazing up and extinction. No temporary star, however, has been observed to reappear in the same celestial place where once had glowed its sudden outburst. But cases are not wanting where incandescence has been both preceded and followed by a continued existence, visible though not brilliant. For such cases as these it is necessary to come down to modern records. We cannot be sure that some faint star has been temporarily brilliant unless we actually see the conflagration itself, or are able to make the identity of the object's precise location in the sky before and after the event perfectly certain by the aid of modern instruments of precision. But no one has ever seen the smoldering fires break out. Temporary stars have always been first noticed only after having been active for hours, if not for days. So we must perforce fall back on instrumental identification by determinations of the star's exact position upon the celestial vault. Some time between May 10th and 12th in the year 1866, the ninth star in the list of known temporaries appeared. It possessed very great light-giving power, being surpassed in brilliancy by only about a score of stars in all the heavens. It retained a maximum luminosity only 3 or 4 days, and in less than 2 months had diminished to a point somewhere between the 9th and 10th magnitudes. In other words, from a conspicuous star, visible to the naked eye, it had passed beyond the power of anything less than a good telescope. Fortunately, we had excellent star catalogues before 1866. These were at once searched, and it was possible to settle quite definitely that a star of about the 9th or 10th magnitude had really existed before 1866 at precisely the same point occupied by the new one. Needless to say, observations were made of the new star itself, and afterward compared with later observations of the faint one that still occupies its place. These render quite certain the identity of the temporary bright star with the faint ones that preceded and followed it. Such results, on the one hand, offer an excellent vindication of the painstaking labor expended on the construction of star catalogues, and on the other, serve to elucidate the mystery of temporary stars. Nothing can be more plausible than to explain by analogy those cases in which no previous or subsequent existence has been observed. It is merely necessary to suppose that, instead of varying from the 9th or 10th magnitude, other temporary objects have begun and ended with the 20th, for the 20th magnitude would be beyond the power of our best instruments. Nor is the star of 1866 an isolated instance. 10 years later, in 1876, a temporary star blazed up to about the 2nd magnitude and returned to invisibility, so far as the naked eye is concerned, within a month, having retained its greatest brilliancy only 1 or 2 days. This star is still visible as a tiny point of light, estimated to be of the 15th magnitude. Whether it existed prior to its sudden outburst can never be known, because we do not possess catalogues including the generality of stars as faint as this one must have been. But at all events, the continued existence of the object helps to place the temporary stars in the class of variables. The next star, already mentioned under nebula, was first seen in 1885. It was in one respect the most remarkable of all, for it appeared almost in the center of the great nebula in the constellation Andromeda. It was never very bright, reaching only the 6th magnitude or thereabouts, was observed during a period of only 6 months, and at the end of that time had faded beyond the reach of our most powerful glasses. It is a most impressive fact that this event occurred within the nebula. Whatever may be the nature of the explosive catastrophe to which the temporary stars owe their origin, we can now say with certainty that not even those vast elemental luminous clouds men call nebulae are free from danger. The last outburst on our records was first noticed February 22, 1901. The star appeared in the constellation Perseus and soon reached the 1st magnitude, surpassing almost every other star in the sky. It has been especially remarkable in that it has become surrounded by a nebulous mass in which are several bright condensations or nuclei, and these seem to be in very rapid motion. The star is still under observation. January 1902. End of chapter 5.
Chapter 6 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Deb K. Practical Talks by an Astronomer by Harold Jacoby. Galileo. Among the figures that stand out sharply upon the dim background of old-time science, there is none that excites a keener interest than Galileo. Most people know him only as a distinguished man of learning, one who carried on a vigorous controversy with the Church on matters scientific. It requires some little study, some careful reading between the lines of astronomical history, to gain acquaintance with the man himself. He had a brilliant, incisive wit, was a genuine humorist, knew well and loved the amusing side of things, and could not often forego a sarcastic pleasantry, or deny himself the pleasure of argument. Yet it is more than doubtful if he ever intended impertinence, or gave willingly any cause of quarrel to the Church. His acute understanding must have seen that there exists no real conflict between science and religion, for time, in passing, has made common knowledge of this truth, as it has of many things once hidden. When we consider events that occurred 3 centuries ago, it is easy to replace excited argument with cool judgment, to remember that those were days of violence and cruelty, that public ignorance was of a density difficult to imagine today, and that it was universally considered the duty of the Church to assume an authoritative attitude upon many questions with which she is not now required to concern herself in the least. Charlatans, unbalanced theorists, purveyors of scientific marvels, were all liable to be passed upon definitely by the Church, not in a spirit of impertinent interference, but simply as part of her regular duties. If the Church's judgment in such matters was sometimes erroneous, if her interference now and again was cruel, the cause must be sought in the manners and customs of the time, when persecution rioted in company with ignorance, and violence was the law. Perhaps even today it would not be amiss to have a modern scientific board pass authoritatively upon novel discoveries and inventions, so as to protect the public against impostors as the Church tried to do of old. Galileo was born at Pisa in 1564. And his long life lasted until 1642, the very year of Newton's birth. His most important scientific discoveries may be summed up in a few words. He was the first to use a telescope for examining the heavenly bodies. He discovered mountains on the moon, the satellites of Jupiter, the peculiar appearance of Saturn, which Owens afterward explained as a ring surrounding the ball of the planet, and finally he found black spots on the sun's disk. These discoveries, together with his remarkable researches in mechanical science, constitute Galileo's claim to immortality as an investigator. But, as we have said, it is not our intention to consider his work as a series of scientific discoveries. We shall take a more interesting point of view, and deal with him rather as a human being, who had contracted the habit of making scientific researches. What must have been his feelings when he first found with his new telescope the satellites of Jupiter? They were seen on the night of January 7th, 1610. He had already viewed the planet through his earlier and less powerful glass, and was aware that it possessed a round disk like the moon, only smaller. Now he saw also 3 objects that he took to be little stars near the planet. But on the following night, as he says, drawn by what fate I know not, the tube was again turned upon the planet. The 3 small stars had changed their positions, and were now all situated to the west of Jupiter, whereas on the previous night 2 had been on the eastern side. He could not explain this phenomenon, but he recognized that there was something peculiar at work. Long afterward, in one of his later works translated into quaint old English by Salisbury, he declared that one sole experiment sufficeth to batter to the ground 1,000 probable arguments. This was already the guiding principle of his scientific activity, a principle of incomparable importance, and generally credited to Bacon. Needless to say, Jupiter was now examined every night. The 9th was cloudy, but on the 10th he again saw his little stars, their number now reduced to 2. He guessed that the 3rd was behind the planet's disk. The position of the 2 visible ones was altogether different from either of the previous observations. On the 11th he became sure that what he saw was really a series of satellites accompanying Jupiter on his journey through space, and at the same time revolving around him. On the 12th, at 3 a.m., he actually saw one of the small objects emerge from behind the planet, and on the 13th he finally saw 4 satellites. 282 years were destined to pass away before any human eye should see a 5th. It was Barnard in 1892 who followed Galileo. To understand the effect of this discovery upon Galileo requires a person who has himself watched the stars, not as a dilettante seeking recreation or amusement, but with that deep reverence that comes only to him who feels, nay knows, that in the moment of observation just past he too has added his mite to the great fund of human knowledge. Galileo's mummified forefinger still points toward the stars from its little pedestal of wood in the Museo at Florence, a sign to all men that he is unforgotten. But Galileo knew on that 11th of January, 1610, that the memory of him would never fade, that the very music of the spheres would thenceforth be attuned to a truer note, if any would but hearken to the Jovian harmony. For he recognized at once that the visible revolution of these moons around Jupiter, while that planet was himself visibly traveling through space, must deal its death blow to the old Ptolemaic system of the universe. Here was a great planet, the center of a system of satellites, and yet not the center of the universe. Surely, then, the earth, too, might be a mere planet like Jupiter, and not the supposed motionless center of all things. The satellite discovery was published in 1610, in a little book called Sidereus Nuncius, usually translated The Sidereal Messenger. It seems to us, however, that the word messenger is not strong enough. Surely in papal Italy a nuncius was more than a mere messenger. He was clothed with the very highest authority, and we think it probable that Galileo's choice of this word in the title of his book means that he claimed for himself similar authority in science. At all events, the book made him at once a great reputation and numerous enemies. But it was not until 1616 that the Holy Office, Inquisition, issued an edict ordering Galileo to abandon his opinion that the earth moved, and that at the same time placed Copernicus's De Revolutionibus and 2 other books advocating that doctrine on the Index Librorum Prohibitorum, or list of books forbidden by the Church. These volumes remained in subsequent editions of the Index down to 1821, but they no longer appear in the edition in force today. Galileo's most characteristic work is entitled The Dialogue on the Two Chief Systems of the World. It was not published until 1632. Although the idea of the book was conceived many years earlier, in it he gave full play to his extraordinary powers as a true humorist, a fine lame among controversialists, and a genuine man of science, valuing naked truth above all other things. As may be imagined, it was no small matter to obtain the authorities' consent to this publication. Galileo was already known to hold heretical opinions, and it was suspected that he had not laid them aside when commanded to do so by the Edict of 1616. But perhaps Galileo's introduction to the dialogue secured the censor's imprimatur. It is even suspected that the Roman authorities helped in the preparation of this introduction. Fortunately, we have a delightful contemporary translation into English, by Thomas Salisbury, printed at London by Leyburn in 1661. We have already quoted from this translation, And now add, from the same work, part of Galileo's masterly preface to the Dialogue. Judicious reader, there was published some years since in Rome a salutiferous edict, that, for the obviating of the dangerous scandals of the present age, imposed a reasonable silence upon the Pythagorean Copernican opinion of the mobility of the earth. There want not such as unadvisedly affirm that the decree was not the production of a sober scrutiny, but of an ill-formed passion. And one may hear some mutter that consultors altogether ignorant of astronomical observations ought not to clip the wings of speculative wits with rash prohibitions. Galileo first states his own views, and then pretends that he will oppose them. He goes on to say that he believes in the earth's immobility, and takes the contrary only for a mathematical capriccio, as he calls it, something to be considered, because possessing an academical interest, but on no account having a real existence. Of course, any one, even a censor, ought to be able to see that it is the capriccio, and not its opposite, that Galileo really advocates. Three persons appear in the Dialogue: Salviati, who believes in the Copernican system; Simplicio, of suggestive name, who thinks the earth cannot move; and finally Sagredus, a neutral gentleman of humorous propensities, who usually begins by opposing Salviati, but ends by being convinced. He then helps to punish poor Simplicio, who is one of those persons apparently incapable of comprehending a reasonable argument. Here is an interesting specimen of the Dialogue, taken from Salisbury's translation. Salviati refers to the argument, then well known, that the earth cannot rotate on its axis, because of the impossibility of its moving along without weariness. Sagredus replies, there are some kinds of animals which refresh themselves after weariness by rolling on the earth, and that therefore there is no need to fear that the terrestrial globe should tire. Nay, it may be reasonably affirmed that it enjoyeth a perpetual and most tranquil repose, keeping itself in an eternal rolling. Salviati's comment on this sally is, you are too tart and satirical, Sagredus. There is no doubt that the Dialogue finished the Ptolemaic theory, and made that of Copernicus the only possible one. At all events, it brought about the well-known attack upon Galileo from the authorities of the Holy Office. We shall not recount the often-told tale of his recantation. He was convicted, very rightly, of being a Copernican, and was forced to abjure that doctrine. Galileo's life may be summed up as one of those through which the world has been made richer. A clean-cutting, analytic wit, never becoming dull, heated again and again in the fierce blaze of controversy, it was allowed to cool only that it might acquire a finer temper, to pierce with fatal certainty the smallest imperfections in the armor of his adversaries. End of Galileo. Recording by Deb K.
Chapter 7 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Betty B. Practical Talks by an Astronomer by Harold Jacoby. Chapter 7. The Planet of 1898. The discovery of a new and important planet usually receives more immediate popular attention and applause than any other astronomical event. Philosophers are fond of referring to our solar system as a mere atom among the countless universes that seem to be suspended within the profound depths of space. They are wont to point out that this solar system, small and insignificant as a whole in comparison with many of the stellar worlds, is, nevertheless, made up of a large number of constituent planets, and these in turn are often accompanied with still smaller satellites or moons. Thus does nature provide worlds within worlds, and it is not surprising that public attention should be at once attracted by any new member of our sun's own special family of planets. The ancients were acquainted with only 5 of the bodies now counted as planets, viz. Mercury, Venus, Mars, Jupiter, and Saturn. The dates of their discovery are lost in antiquity. To these, Uranus was added in 1781 by a brilliant effort of the elder Herschel. We are told that intense popular excitement followed the announcement of Herschel's first observation. He was knighted and otherwise honored by the English king, and was enabled to lay a secure foundation for the future distinguished astronomical reputation of his family. Herschel's discovery quickened the restless activity of astronomers. Persistent efforts were made to sift the heavens more and more closely, with the strengthened hope of adding still further to our planetary knowledge. An association of 24 enthusiastic German astronomers was formed for the express purpose of hunting planets, but it fell to the lot of an Italian, Piazzi, of Palermo, to find the first of that series of small bodies now known as the asteroids, or minor planets. He made the discovery at the very beginning of our century, January 1st, 1801. But news traveled slowly in those days, and it was not until nearly April that the German observers heard from Piazzi. In the meantime he had himself been prevented by illness from continuing his observations. Unfortunately, the planet had by this time moved so near the sun, on account of its own motions and those of the earth, that it could no longer be observed. The bright light of the sun made observations of the new body impossible, and it was feared that, owing to lack of knowledge of the planet's orbit, astronomers would be unable to trace it. So there seemed indeed to be danger of an almost irreparable loss to science. But in scientific, as in other human emergencies, someone always appears at the proper moment. A very young mathematician at Göttingen, named Gauss, attacked the problem, and was able to devise a method of predicting the future course of the planet on the sky, using only the few observations made by Piazzi himself. Up to that time no one had attempted to compute a planetary orbit, unless he had at his disposal a series of observations extending throughout the whole period of the planet's revolution around the sun. But the Piazzi planet offered a new problem in astronomy. It had become imperatively necessary to obtain an orbit from a few observations made at nearly the same date. Gauss's work was signally triumphant, for the planet was actually found in the position predicted by him, as soon as a change in the relative places of the planet and earth permitted suitable observations to be made. But after all, Piazzi's planet belongs to a class of quite small bodies, and is by no means as interesting as Herschel's discovery, Uranus. Yet even this must be relegated to second rank among planetary discoveries. On September 23, 1846, the telescope of the Berlin Observatory was directed to a certain point on the sky for a very special reason. Gall, the astronomer of Berlin, had received a letter from Leverrier of Paris, telling him that if he would look in a certain direction he would detect a new and large planet. Leverrier's information was based upon a mathematical calculation. Seated in his study, with no instruments but pen and paper, he had slowly figured out the history of a world as yet unseen. Tiny discrepancies existed in the observed motions of Herschel's planet Uranus. No man had explained their cause. To Leverrier's acute understanding, they slowly shaped themselves into the possible effects of attraction emanating from some unknown planet exterior to Uranus. Was it conceivable that these slight tremulous imperfections in the motion of a planet could be explained in this way? Leverrier was able to say confidently yes, but we may rest assured that Gall had but small hopes that upon his eye first of all the myriad eyes of men would fall a ray of the new planet's light. Careful and methodical, he would neglect no chance of advancing his beloved science. He would look. Only one who has himself often seen the morning sunrise put an end to a night's observation of the stars can hope to appreciate what Gall's feelings must have been when he saw the planet. To his trained eye it was certainly recognizable at once. And then the good news was sent on to Paris. We can imagine Leverrier, the cool calculator, saying to himself, "Of course he found it. It was a mathematical certainty." Nevertheless, his satisfaction must have been of the keenest. No triumphs give a pleasure higher than those of the intellect. Let no one imagine that men who make researches in the domain of pure science are underpaid. They find their reward in pleasure that is beyond any price. The Leverrier planet was found to be the last of the so-called major planets, so far as we can say in the present state of science. It received the name Neptune. Observers have found no other member of the solar system comparable in size with such bodies as Uranus and Neptune. More than one eager mathematician has tried to repeat Leverrier's achievement, but the supposed planet was not found. It has been said that the figures never lie, yet such is the case only when the computations are correctly made. People are prone to give to the work of careless or incompetent mathematicians the same degree of credence that is really due only to masters of the craft. It requires the test of time to affix to any man's work the stamp of true genius. While then we have found no more large planets, quite a group of companions to Piazzi's little one have been discovered. They are all small, probably never exceeding about 400 miles in diameter. All travel around the sun in orbits that lie wholly within that of Jupiter, and are exterior to that of Mars. The introduction of astronomical photography has given a tremendous impetus to the discovery of these minor planets, as they are called. It is quite interesting to examine the photographic process by which such discoveries are made possible and even easy. The matter will not be difficult to understand if we remember that all the planets are continually changing their places among the other stars. For the planets travel around the sun at a comparatively small distance. The great majority of the stars, on the contrary, are separated from the sun by an almost immeasurable space. As a result, they do not seem to move at all among themselves, and so we call them fixed stars. They may indeed be in motion, but their great distance prevents our detecting it in a short period of time. Now, stellar photographs are made in much the same way as ordinary portraits. Only instead of using a simple camera, the astronomer exposes his photographic plate at the eye end of a telescope. The sensitive surface of the plate is substituted for the human eye. We then find on the picture a little dot corresponding to every star within the photographed region of the sky. But, as everyone knows, the turning of the earth on its axis makes the whole heavens, including the sun, moon, and stars, rise and set every day. So the stars, when we photograph them, are sure to be either climbing up in the eastern sky or else slowly creeping down in the western, and that makes astronomical photography very different from ordinary portrait work. The stars correspond to the sitter, but they don't sit still. For this reason it is necessary to connect the telescope with a mechanical contrivance which makes it turn round like the hour hand of an ordinary clock. The arrangement is so adjusted that the telescope, once aimed at the proper object in the sky, will move so as to remain pointed exactly the same during the whole time of the photographic exposure. Thus, while the light of any star is acting on the plate, such action will be continuous at a single point. Consequently, the finished picture will show the star as a little dot, while without this arrangement the star would trail out into a line instead of a dot. Now we have seen that the planets are all moving slowly among the fixed stars. So if we make a star photograph in a part of the sky where a planet happens to be, the planet will make a short line on the plate, whereas if the planet remained quite unmoved relatively to the stars, it would give a dot like the star dots. The presence of a line, therefore, at once indicates a planet. This method of planet hunting has proved most useful. More than 400 small planets similar to Piazzi's have been found, though never another one like Uranus and Neptune. As we have said, all these little bodies lie between Mars and Jupiter. They evidently belong to a group or family, and many astronomers have been led to believe that they are but fragments of a former large planet. In August 1898, however, one was found by Witt of Berlin, which will probably occupy a very prominent place in the annals of astronomy. for this planet goes well within the orbit of Mars, and this will bring it at times very close to the earth. In fact, when the motions of the new planet and the earth combine to bring them to their positions of greatest proximity, the new planet will approach us closer than any other celestial body except our own moon. Witt named his new planet Eros. Its size, though small, may prove to be sufficient to bring it within the possibilities of naked eye observation at the time of closest approach to the earth. To astronomers, the great importance of this new planet is due to the following circumstance. For certain reasons too technical to be stated here in detail, the distance from the earth to any planet can be determined with a degree of precision which is greatest for planets that are near us. Thus, in time, we shall learn the distance of Eros more accurately than we know any other celestial distance. From this, by a process of calculation, the solar distance from the earth is determinable. But the distance from earth to sun is the fundamental astronomical unit of measure, so that Witt's discovery, through its effect on the unit of measure, will doubtless influence every part of the science of astronomy. Here we have once more a striking instance of the reward sure to overtake the diligent worker in science. A whole generation of men will doubtless pass away before we shall have exhausted the scientific advantages to be drawn from Witt's remarkable observation of 1898. End of chapter 7.
Chapter 8 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Practical Talks by an Astronomer by Harold Jacoby. How to make a sundial. This chapter is especially intended for boys and girls and others who like to make things with carpenter's tools. Long before clocks and watches had been invented, people began to measure time with sundials. Nowadays, when almost everyone has a watch in his pocket, and can have a clock, too, on the mantelpiece of every room in the house, the sundial has ceased to be needed in ordinary life. But it is still just as interesting as ever to anyone who would like to have the means of getting time direct from the sun, the great hour hand, or timekeeper of the sky. Any person who is handy with tools can make a sundial quite easily by following the directions given below. In the first place, you must know that the sundial gives the time by means of the sun's shadow. If you stick a walking cane up in the sand on a bright sunshiny day, the cane has a long shadow that looks like a dark line on the ground. Now, if you watch this shadow carefully, you will see that it does not stay in the same place all day. Slowly but surely, as the sun climbs up in the sky, the shadow creeps around the cane. You can see quite easily that if the cane were fastened in a board floor, and if we could mark on the floor the places where the shadow was at different hours of the day, we could make the shadow tell us the time, just like the hour hand of a clock. A sundial is just such an arrangement as this, and I will show you how to mark the shadow places exactly, so as to tell the right time without any trouble whenever the sun shines. If you were to watch very carefully such an arrangement as a cane standing in a board floor, you would not find the creeping shadow in just the same place at the same time every day. If you marked the place of the shadow at exactly 10 o'clock by your watch some morning, and then went back another day at 10, you would not find the shadow on the old mark. It would not get very far from it in a day or two, but in a month or so it would be quite a distance away. Now, of course, a sundial would be of no use if it did not tell the time correctly every day, and in fact it is not easy to make a dial when the shadow is cast by a stick standing straight up. But we can get over this difficulty very well by letting the shadow be cast by a stick that leans over toward the floor just the right amount, as I will explain in a moment. Of course, we should not really use the floor for our sundial. It is much better to mark out the hour lines, as they are called, on a smooth piece of ordinary white board, and then, after the dial is finished, It can be screwed down to a piazza floor or railing, or it can be fastened on a window sill. It ought to be put in a place where the sun can get at it most of the time, because, of course, you cannot use the sundial when the sun is not shining on it. If the dial is set on a window sill, of a city house for instance, you must choose a south window if you can, so as to get the sun nearly all day. If you have to take an east window, you can use the dial in the morning only, and in a west window only in the afternoon. Sometimes it is best not to try to fasten the dial to its support with screws, but just to mark its place, and then set it out whenever you want to use it. For if the dial is made of wood and not painted, it might be injured by rain or snow in bad weather if left out on a window sill or piazza. It is not quite easy to fasten a little stick to a board so that it will lean over just right. So it is better not to use a stick or a cane in the way I have described, but instead to use a piece of board cut to just the right shape. Figure 1 shows what a sundial should look like. The lines to show the shadow's place at the different hours of the day will be marked on the board with capitals A, B, C, D, and this will be put flat on the window sill or piazza floor. The three-cornered piece of board, small letter A, B, C, is fastened to the bottom board, capital A, B, C, D, by screws going through capital A, B, C, D from underneath. The edge AB of the three-cornered board, ABC, then takes the place of the leaning stick or cane, and the time is marked by the shadow cast by the edge AB. Of course, it is important that this edge should be straight and perfectly flat and even. If you are handy with tools, you can make it quite easily. But if not, you can mark the right shape on a piece of paper very carefully, and take it to a carpenter, who can cut the board according to the pattern you have marked on the paper. Now I must tell you how to draw the shape of the three-cornered board ABC. Figure 2 shows how it is done. The side AC should always be just 5 inches long. The side BC is drawn at right angles to AC, which you can do with an ordinary carpenter's square. The length of BC depends on the place for which the dial is made. The following table gives the length of BC for various places in the United States, and after you have marked out the length of BC, it is only necessary to complete the three-cornered piece by drawing the side AB from A to B. Table showing the length of the side BC in inches. Albany, 4 11/16. Baltimore, 4 1/16. Boston, 4 1/2. Buffalo, 4 11/16. Charleston, 3 1/4. Chicago, 4 1/2. Cincinnati, 4 1/16. Cleveland, 4 1/2. Denver, 4 3/16. Detroit, 4 1/2. Indianapolis, 4 1/16. Kansas City, 3 15/16. Louisville, 3 15/16. Milwaukee, 3 11/16. New Orleans, 2 7/8. New York, 4 3/8. Omaha, 4 3/8. Philadelphia, 4 3/16. Pittsburgh, 4 3/8. Portland, Maine, 4 13/16. Richmond, 3 15/16. Rochester, 4 11/16. San Diego, 3 1/4. San Francisco, 3 15/16. Savannah, 3 1/8. St. Louis, 3 15/16. St. Paul, 5. Seattle, 5 9/16. Washington, D.C., 4 1/16. If you wish to make a dial for a place not given in the table, it will be near enough to use the distance BC as given for the place nearest to you. But in selecting the nearest place from the table, please remember to take that one of the cities mentioned which is nearest to you in a north and south direction. It does not matter how far away the place is in an east and west direction. So, instead of taking the place that is nearest to you on the map in a straight line, take the place to which you could travel by going principally east or west, and very little north or south. The figure drawn is about the right shape for New York. The board used for the three-corner piece should be about 1/2 inch thick, but if you are making a windowsill dial, you may prefer to have it smaller than I have described. You can easily have it half as big by making all the sizes and lines in 1/2 inches where the table calls for inches. After you have marked out the dimensions for the three-cornered piece that is to throw the shadow, you can prepare the dial itself, with the lines that mark the place of the shadow for every hour of the day. This you can do in the manner shown in Figure 3. Just as in the case of the three-cornered piece, you can draw the dial with a pencil directly on a smooth piece of white board, about 3/4 of an inch thick, or you can mark it out on a paper pattern and transfer it afterward to the board. Perhaps it will be as well to begin by drawing on paper, as any mistakes can then be corrected before you commence to mark your wood. In the first place you must draw a couple of lines MN and M''N', 8 inches long and just far enough apart to fit the edge of your three-cornered shadow piece. You will remember I told you to make that 1/2 inch thick, so your two lines will also be 1/2 inch apart. Now draw the two lines NO and N'O', square with MN and M''N', and make the distances NO and N'O' just 5 inches each. The lines OK, O', and the other lines forming the outer border of the dial are then drawn just as shown, OK and O'K' being just 8 inches long, the same as MN and M'N'. The lower lines in the figure, which are not very important, are to complete the squares. You must mark the lines NO and N'O' with the figures VI, these being the lines reached by the shadow at 6 o'clock in the morning and evening. The points where the VII, VIII, and other hour lines cut the lines OK, O'K', MK, and M'K' can be found from the table on page 78. In using the table you will notice that the line IX falls sometimes on one side of the corner K and sometimes on the other. Thus for Albany the line passes 7 7/16 inches from O, while for Charleston it passes 4 3/8 inches from M. For Baltimore it passes exactly through the corner K. Table showing how to mark the hour lines. Albany, distance in inches from O to the line marked VII, 1 15/16. From O to the line marked VIII, 4 3/16. From O to the line marked IX, 7 7/16. From M to the line marked X, 3 1/16. From M to the line marked XI, 1 7/16. Baltimore, distance in inches from O to the line marked VII, 2 1/8. From O to the line marked VIII, 4 11/16. From O to the line marked IX, 8. From M to the line marked X, 2 7/8. From M to the line marked XI, 1 7/16. Boston, distance in inches from O to the line marked VII, 2. From O to the line marked VIII, 4 5/16. from O to the line marked IX, 7 7/16, from M to the line marked X, 3 1/16, from M to the line marked XI, 1 7/16. Buffalo, distance in inches from O to the line marked VII, 1 15/16, from O to the line marked VIII, 4 3/16, from O to the line marked IX, 7 7/16, from M to the line marked X, 3 1/16, from M to the line marked XI, 1 7/16. Charleston, distance in inches from O to the line marked VII, 2 7/16, from O to the line marked VIII, 5 3/8, distance from M to the line marked IX, 4 3/8, from M to the line marked X, 2 1/2, from M to the line marked XI, 1 1/8. Chicago, distance in inches from O to the line marked VII, 2, from O to the line marked VIII, 4 5/16, from O to the line marked IX, 7 7/16, from M to the line marked X, 3 1/16, from M to the line marked XI, 1 7/16. Cincinnati, distance in inches from O to the line marked VII, 2 1/8, from O to the line marked VIII, 4 11/16, from O to the line marked IX, 8, from M to the line marked X, 2 7/8, from M to the line marked XI, 1 7/16. Cleveland, distance in inches from O to the line marked VII, 2, from O to the line marked VIII, 4 5/16, from O to the line marked IX, 7 7/16, from M to the line marked X, 3 1/16, from M to the line marked XI, 1 7/16. Denver, distance in inches from O to the line marked VII, 2 1/8, from O to the line marked VIII, 4 1/2, from O to the line marked IX, 7 11/16, from M to the line marked X, 2 7/8, from M to the line marked XI, 1 7/16. Detroit, distance in inches from O to the line marked VII, 2, from O to the line marked VIII, 4 5/16, from O to the line marked IX, 7 7/16, from M to the line marked X, 3 1/16, from M to the line marked XI, 1 7/16. Indianapolis, distance in inches from O to the line marked VII, 2 1/8, from O to the line marked VIII, 4 11/16, from O to the line marked IX, 8, from M to the line marked X, 2 7/8, from M to the line marked XI, 1 7/16. Kansas City, distance in inches from O to the line marked VII, 2 1/4, from O to the line marked VIII, 4 11/16, from O to the line marked IX, 8, from M to the line marked X, 2 7/8, from M to the line marked XI, 1 5/16. Louisville, distance in inches from O to the line marked VII, 2 1/4, from O to the line marked VIII, 4 and 11/16, from O to the line marked IX, 8, from M to the line marked X, 2 and 7/8, from M to the line marked XI, 1 and 5/16. Milwaukee, distance in inches from O to the line marked VII, 1 and 15/16, from O to the line marked VIII, 4 and 3/16, from O to the line marked IX, 7 and 7/16, from M to the line marked X, 3 and 1/16, from M to the line marked XI, 1 and 7/16. New Orleans, distance in inches from O to the line marked VII, 2 and 11/16, from O to the line marked VIII, 5 and 3/4, distance from M to the line marked IX, 4 and 1/16, from M to the line marked X, 2 and 5/16, from M to the line marked XI, 1 and 1/8. New York, distance in inches from O to the line marked VII, 2, from O to the line marked VIII, 4 and 5/16, from O to the line marked IX, 7 and 11/16, from M to the line marked X, 3 and 1/16, from M to the line marked XI, 1 and 7/16. Omaha, distance in inches from O to the line marked VIII, 2, from O to the line marked VIII, 4 and 5/16, from O to the line marked IX, 7 and 11/16, from M to the line marked X, 3 and 1/16, from M to the line marked XI, 1 and 7/16. Philadelphia, distance in inches from O to the line marked VIII, 2 and 1/8, from O to the line marked VIII, 4 and 1/2, from O to the line marked IX, 7 and 11/16, from M to the line marked X, 2 and 7/8, from M to the line marked XI, 1 and 7/16. Pittsburgh, distance in inches from O to the line marked VIII, 2, from O to the line marked VIII, 4 and 5/16, from O to the line marked IX, 7 and 11/16, from M to the line marked X, 3 and 1/16, from M to the line marked XI, 1 and 7/16. Portland, Maine, distance in inches from O to the line marked VIII, 1 and 15/16, from O to the line marked VIII, 4 and 3/16, from O to the line marked IX, 7 and 1/8, from M to the line marked X, 3 and 3/16, from M to the line marked XI, 1 1/2. Richmond, distance in inches from O to the line marked VIII, 2 1/4, from O to the line marked VIII, 4 and 11/16, from O to the line marked IX, 8, from M to the line marked X, 2 and 7/8, from M to the line marked XI, 1 and 5/16. Rochester, distance in inches from O to the line marked VIII, 1 and 15/16, from O to the line marked VIII, 4 and 3/16, from O to the line marked IX, 7 and 7/16, from M to the line marked X, 3 and 1/16, from M to the line marked XI, 1 and 7/16. San Diego, Distance in inches from O to the line marked VII, 2 7/16. From O to the line marked VIII, 5 3/8. Distance from M to the line marked IX, 4 3/8. From M to the line marked X, 2 1/2. From M to the line marked XI, 1 1/8. San Francisco. Distance in inches from O to the line marked VII, 2 1/4. From O to the line marked VIII, 4 11/16. From O to the line marked IX, 8. From M to the line marked X, 2 7/8. From M to the line marked XI, 1 5/16. Savannah. Distance in inches from O to the line marked VII, 2 9/16. From O to the line marked VIII, 5 9/16. Distance from M to the line marked IX, 4 1/4. From M to the line marked X, 2 1/2. From M to the line marked XI, 1 1/8. St. Louis. Distance in inches from O to the line marked VII, 2 1/4. From O to the line marked VIII, 4 11/16. From O to the line marked IX, 8. From M to the line marked X, 2 7/8. From M to the line marked XI, 1 5/16. St. Paul. Distance in inches from O to the line marked VII, 1 15/16. From O to the line marked VIII, 4 1/16. From O to the line marked IX, 7 1/8. From M to the line marked X, 3 3/16. From M to the line marked XI, 1 1/2. Seattle. Distance in inches from O to the line marked VII, 1 13/16. From O to the line marked VIII, 3 15/16. From O to the line marked IX, 6 5/8. From M to the line marked X, 3 3/8. From M to the line marked XI, 1 1/2. Washington, D.C. Distance in inches from O to the line marked VII, 2 1/8. From O to the line marked VIII, 4 11/16. From O to the line marked IX, 8. From M to the line marked X, 2 7/8. From M to the line marked XI, 1 7/16. The distance for the line marked V from O' is just the same as the distance from O to VII. Similarly, IV corresponds to VIII, III to IX, II to X, and I to XI. The number XII is marked at MM' as shown. If you desire to add lines, not shown in Figure 3 to avoid confusion, for hours earlier than 6 in the morning, it is merely necessary to mark off a distance on the line KO below the point O, and equal to the distance from O to VII. This will give the point where the 5 a.m. shadow line drawn from N cuts the line KO. A corresponding line for 7 p.m. can be drawn from N' on the other side of the figure. After you have marked out the dial very carefully, you must fasten the 3-cornered shadow piece to it in such a way that the whole instrument will look like Figure 1. The edge AC goes on NM. The point A must come exactly on N, and as the lines NM, and N''M' have been made just the right distance apart to fit the thickness of the three-cornered piece ABC, everything will go together just right. The point C will not quite reach to M, but will be on the line NM, at a distance of 3 inches from M. The two pieces of wood will be fastened together with 3 screws going through the bottom board ABCD, and into the edge AC of the three-cornered piece. The whole instrument will then look something like Figure 1. After you have got your sundial put together, you need only set it in the sun, in a level place, on a piazza or window-sill, and turn it round until it tells the right time by the shadow. You can get your local time from a watch near enough for setting up the dial. Once the dial is set right, you can screw it down or mark its position, and it will continue to give correct solar time every day in the year. If you wish to adjust the dial very closely, you must go out some fine day and note the error of the dial by a watch at about 10 in the morning, and at noon, and again at about 2 in the afternoon. If the error is the same each time, the dial is rightly set. If not, you must try, by turning the dial slightly, to get it placed so that your 3 errors will be nearly the same. When you have got them as nearly alike as you can, the dial will be sufficiently near right. The solar or dial time may, however, differ somewhat from ordinary watch time, but the difference will never be great enough to matter, when we remember that sundials are only rough timekeepers after all, and useful principally for amusement. End of Chapter 8.